Hi everyone. Today, I'm going to present our work titled PatchScaler, an efficient patch-independent diffusion model for image super-resolution. This work is a collaboration between Zhenjiao University, ByteDance, and Nanjing University of Science and Technology. Here's the outline of today's talk. I'll begin with the background of single-image super-resolution and the challenges of current methods. Then, I'll introduce our proposed method, PatchScaler, followed by experiments and evaluations. Finally, I'll summarize our contributions and discuss potential future directions. Single Image Super-Resolution, or SISR, aims to reconstruct high-resolution images from low-resolution inputs. It's a fundamental task in computer vision, with wide applications such as security surveillance, entertainment, compressed image recovery, object detection, and remote sensing. However, previous single-image super-resolution methods faces two main challenges in diffusion-based models. First, these models require many sampling steps, which makes them slow and computationally expensive. Second, most methods apply the same sampling strategy to all regions, regardless of complexity. Some patches are easy to reconstruct, while others are highly complex, leading to wasted computation. This leads to inefficiencies and unnecessary computation. Our key insight is that not all patches are born equal. Some parts of the image can be reliably reconstructed with fewer steps, while others require more. Imagine a sky patch with smooth color gradients compared to a patch filled with detailed foliage. The sky can be restored quickly, while the foliage needs longer sampling to recover its fine structures. Hence, we propose an adaptive, patch-wise sampling method. We assign different sampling efforts to patches based on their reconstruction difficulty. This saves computational resources while maintaining or even improving the perceptual quality of the output. PatchScaler introduces two key innovations. The first is patch-adaptive group sampling, which allocates different numbers of sampling steps according to patch difficulty. The second is the texture prompt, which leverages external texture priors to enhance fine detail reconstruction. The goal of PatchScaler is to balance efficiency and perceptual quality, a trade-off that is often difficult to achieve in diffusion-based SISR. The first module of PatchScaler is the Global Restoration Module. Specifically, we apply our Global Restoration Module to produce a coarse high-resolution feature map along with a confidence map. This confidence map plays a crucial role. It predicts, for every location, how close the coarse reconstruction is likely to be to the ground truth. If the confidence is high, the difference between coarse and ground truth features is small. If it's low, the difference is large. By averaging the confidence scores within each spatial patch, we produce what we call a quantified confidence map, or CMAP. The CMAP essentially classifies patches into categories of reconstruction difficulty: simple, medium, or hard based on chosen thresholds. Then, we introduce patch-adaptive group sampling (PGS). Once every patch is grouped in above way, we assign different sampling trajectories for each group. This corresponds to creating shortcut paths in the diffusion process. For patches with high confidence, those classified as simple, we can skip a large portion of the denoising trajectory and start the reverse process much later, requiring only a small number of steps. For medium patches, we start earlier with a moderate number of steps. For hard patches, where the coarse reconstruction is still far from the ground truth, we assign the full trajectory and the most iterations. In other words, instead of following a one-size-fits-all process, we allow individual patches to follow their own optimized diffusion paths depending on their difficulty. Here you can see examples of how PGS accurately identifies different regions based on their difficulty. This adaptive grouping ensures efficient use of computation and improves overall restoration quality. Furthermore, when we designed PatchScaler, another critical challenge we encountered was the misalignment between image inputs and text prompts, which is a common issue when applying diffusion models to low-level vision tasks like super-resolution. To address this, we proposed the texture prompt, tailored specifically for super-resolution. At its core is the reference texture memory (RTM), built offline before inference. The RTM contains a compact yet representative set of high-quality texture patches from diverse categories: animals, plants, sky, architecture, and illustrations collected from datasets like Div Haruke, outdoor scene training, and manga 109. After clustering and downsampling, we retain only about 2,000 texture pairs, ensuring efficient retrieval without adding cost during inference. During inference, a coarse patch from the low-resolution image is projected into a semantic embedding space and compared with all keys in the RTM. The top K most relevant textures are retrieved and fed into a similarity-aware texture encoder, which attaches to our PatchDT backbone. Through cross-attention, these encoded texture priors are injected during denoising, guiding the model to reconstruct realistic fine-grained details. Now let's move on to experiments. We evaluate PatchScaler against state-of-the-art SISR methods on both synthetic and real-world datasets. Our model outperforms others in perceptual quality metrics such as MAN-IQ, Clipica, and music. In terms of efficiency, PatchScaler significantly reduces the runtime. It's up to 4 times faster than previous diffusion models like Redshift. Moreover, our method supports multi-GPU parallelism, enabling even faster inference. Here are visual comparisons on real-world low-resolution images. PatchScaler produces sharper textures and more realistic results compared to other methods, which often appear blurry or oversmoothed. More experimental analysis can be found in our paper. To conclude, PatchScaler offers an efficient and perceptually strong solution for image super-resolution. By combining adaptive sampling and texture prompts, our PatchScaler achieves both speed and quality. In the future, we plan to explore sampling distillation techniques and enhance deployment efficiency for real-world applications. Thank you for your attention.